Welcome viewers to our second lecture on dimensions. Let us see three cases where I'll explain about dimensions and how these should be balanced on the both sides of an equivalence relation. Now in first case, this is force which is proportional to the product of two masses and the square of the distance between them. It is in normal language said that the gravitational force between two bodies is directly proportional to the product of their masses and inversely proportional to the square of the distance between them, and the direction of the force is directed always towards the center of these two masses. Now if we say that F is proportional to M and M, then F is inversely proportional to 1 upon R square, then F is proportional to M upon R square, or F is equal to GMM upon R square. Now we know that the dimension of the force are M1 L1 T minus 2, and the dimension of mass is mass into mass is 1 plus 1 mass 2 and R2. Now this is G M2, and because it is in the denominator, so it will be L minus 2. Therefore the dimension of G, in order to balance the dimensions on the left hand side and the right hand side, would be G is equal to M1 L3 T minus 2, so that M1 L1 T minus 2 is equal to M2 L minus 2 M minus 1 L cube T minus 2, so that after adjusting the indices we get M1 L1 T minus 2 and M1 L1 T minus 2 on both sides. Now we will also see the energy of a falling body. The energy of a falling body is given by E is equal to kinetic energy plus potential energy. Now the dimensions of energy are M L2 T minus 2, and the dimension of kinetic energy would be M L square upon T square plus M L T minus 2. Now H is L, H is height, that is length. Now M1 L2 T minus 2 would be equals to half M L2 T minus 2 plus M1 L2 T minus 2. Here we see that the dimensions of all the terms are equal. We have to always see that if the expression is multi-terms, then the dimension of each terms must be equal, otherwise the relation is not valid. Now we see the third case. Volume of a sphere is given by 4 upon 3 pi r cube. Now volume is given by length, breadth into height. Now length means L, breadth means also L, and height is also L. So it is L cube, L3. Dimension is L3, and there is no M, so I put it M0, and T is also not there, so I'll put it T also 0. Then 4 upon 3 pi L3 and 0 and T0. Now in these three cases we see that there are three kinds of constants. One is G, one is half, and the third one is 4 upon 3 pi. But all these constants are of different nature. G is a universal gravitational constant, but it is not dimensionless, it has dimension. What are its dimensions? Its dimensions are m minus 1 L cube T minus 2. Now, as far as half is concerned, half is a numeral and it has no physical direction. It neither has length nor mass nor time. The volume where we get the dimensions as L cube is equal to 4 by 3 pi L cube. Now in this case, pi is what? Pi is circumference upon diameter, that is length upon length. So what we get is L1 minus 1, that is L0. But pi is not a number. We must keep it always in mind that there are three kinds of constants. One is numeral. Numeral is a number, any kind of number. It could be a real number, natural number, whole number, rational number, irrational number, whatever kind the number is. Numeral is just number. It is a count only. It has no physical dimension. It does not have either length or mass or time. So it is dimensionless. This is type of constants. Now, the second type of constants are physical constant such as G, H, C. So C is what? C is x upon t. Therefore, its dimensions are L, T minus 1. But it is a constant. We cannot have anybody which can move at higher velocity than the velocity of light, that is c. So c is invariant, it is a constant. It is a universal constant. Rather, it is a limit. Therefore, we have seen two kinds of dimensions. One is numeral, which does not have any dimension at all. The second case is where we have constants, where the dimension is there, but these are constants. These are normally used to normalize the equation, to balance the equation on two sides. These are constants with dimensions. The other case is like G. The dimensions of G are m minus 1 L cube and T minus 2. Here we see that G is a constant, a universal constant, but it has a dimension like C has a dimension. Or we can see another constant like E is equal to H nu. So E has dimensions of M L2 T minus 2 H. The dimension of frequency would be T minus 1. So in order to balance the two sides, the H must have dimensions of M L2 T minus 1. So H is a constant which is known as Planck's constant, but it has also dimensions of mass 1 time, length 2 times, and t minus 1 time. Now the third kind of dimensions are, third kind of constants are dimension neutral. These are constants where the constant has a dimension which are equal in denominator and numerator, so that it becomes neutral, like pi. Pi is what? Pi is circumference c upon diameter. C upon phi, C upon diameter. And what is C? C is length, length of something, length of circumference. L upon, and diameter is also given by length, L upon L. That is L1 into L minus 1, or L one minus 1, or L0. So pi has no dimension in the sense that it is dimension neutral, but it is not a number. Though pi is a constant, but it is not a number in the sense the numerals are. Numerals are only counting. The other constant which has dimensions, they are used, or they always represent some physical idea, and they have to be used in order to balance the dimensions. The third kind of constants are which are dimension neutral, like pi. Pi is c upon 5, that is circumference upon diameter, L upon L, L1, L minus 1, that becomes L1 minus 1, L0, that is the dimension is non-neutral. But pi should not be misunderstood as a number. Pi is a ratio, a constant ratio, a universal ratio. Whatever be the value of circumference and what the ratio of the diameter and its circumference will always be pi. So these are the three types of constants, and we have seen that whatever be the case, when there is equivalence relation, it should be balanced dimensionally on the both sides. Thank you for watching the video.